hope to teach you a little bit about what we're doing today. I want to start by acknowledging the support that we got from the eScience Foundation. This work was only possible. Hold on a second. Yes, this work was only really possible thanks to the support from the AI UW seed grant from the eScience Foundation. And you're only going to hear from two people during this talk, myself and Medha. This was really an interdisciplinary project that brought together lots of different departments from UW. And although you're only going to hear from us, people that you see on the screen were like crucial for making this project work. You're going to hear from Medha in a moment, and I'll pass it over to her in about 10 minutes. But I want to start the presentation by telling you a little bit of a story. So about 10 years ago, I started working with animals in sub-Saharan Africa. And back then, I was baby-faced, I was marginally less gray, I was a little bit more optimistic. And one day, in my youthful optimism, I drove into what you could only call a swamp when I was following a group of lions. And I remember this very, very well. I remember the vehicle slowly stopping. I remember the vehicle slowly sinking. I remember the lions like disappearing into the sunset. And then I spent about 7 hours trying to get myself out of this mess, which I can tell you about if you ask me later. And I mention this now because it was during that period of time, over the course of these many different strandings, that I really began to appreciate the value of biologgers. So these are sensors that we put out onto animals to understand where they're going and to try and figure out why. So for those of you that don't know me, again, my name is Kasim. I'm a wildlife scientist within the Abrams Lab within the Center for Ecosystem Sentinels. And within this group, we're very much interested in understanding how the behaviors of animals, from penguins to whales to African carnivores, is being impacted by global environmental change and what the consequences of that are for interactions between species and interactions between wildlife and people. And we look at these questions with the help of fieldwork, with the help of these wearable sensors that we deploy in these animals, and through collaborations, both research and technical, to try and answer some of these questions. And so today, in this afternoon, you're going to hear from Medha and myself about a specific project where we try to figure out the behaviors of these animals using sensors that we put out on predators in the wild. And in a few minutes, you're going to hear from Medha about exactly how we did this behavior classification. But before we do that, I wanted to tell you about why. Like, why are we even interested in trying to figure out what animals are doing? And it all really starts with movement. So animal movements are incredibly important. They shape an animal's ability to find mates. They can impact disease transmission between animals and between animals and people. And they impact the delivery of key ecosystem services like pollination. And through its impact on movement, climate can impact a whole range of processes that impact the survival of species and also the systems that they find themselves in. But the environments that these animals are in isn't the only thing that drives how they move. That's also driven by their internal states. And one of these is hunger. So if any of you are anything like me, and I can almost guarantee maybe half of you in the room are, when you're hungry, you make very, very different decisions than when you're full. And that's normal because from the tiniest bacteria to like the most iconic predators, hunger, this drive to acquire energy, is a very, very powerful motivator. The problem is that when it comes to looking at how these latent states, these things that you can't see like hunger, how they interact with these long-term environmental processes like climate to shape the behavior and the movements of these animals, that field is relatively new. But it's really important to bridge that understanding of how these things come together in order to understand the ways in which climate impacts species and how some of those impacts might change in the future. And in our group in the Abrams Lab, we're particularly interested in trying to understand this for top predators. Now, many of these species that you see here, they're keystone predators. They're really important for ecosystem functioning. And many of them are experiencing or will experience at some point some sort of environmental change in the coming decades. And so we use one of these species in particular that we're going to talk about today to try and bridge this gap. And that's the African wild dog. So this is an endangered large carnivore. It's pack living and it's found in sub-Saharan Africa. It's a keystone species, so it plays this really, really important role in the systems that you find it in. And they're an excellent choice for studying how climate impacts the behavior of these animals because they're really sensitive to environmental change. We know from other studies that their survival is impacted by things like temperature, but we don't know the specific pathways through which those mechanisms are acting. So in this work, we're really trying to understand how these things come together to shape the movements of this top predator species. Now, the challenge is that in order to build this mechanistic understanding of how these different pieces are shaping the behaviors of these animals, you need a lot of data. You need a lot of it. You need data on the movements of these animals. You need data on the environments that these animals are experiencing. And you need data on the internal states, like hunger of these animals. And that is incredibly, incredibly difficult to get. But the good news is that members of the Abrams Lab have been working within the system for decades. We have over a decade's worth of experience putting out sensors onto these animals to collect this movement data. And we're partners with one of the longest running conservation organizations in Botswana. And through these collaborations and through the immense effort that we've put in, we have access to a really rich data set to try and tease apart some of these things that are happening. And so this data set, which I'll speak on in a moment, comes from the Okavango Delta. The Delta is one of the world's most iconic inland delta systems. It's a World Heritage Site, and it's a really nice area to look at these sorts of questions because it's also experiencing rapid environmental change as a result of the climate crisis. So Botswana Predator Conservation is our partner organization. They've been operating a field site there since the 90s. And it was founded by someone from Seattle, Tico McNutt. And this data set that we have access to and that we've helped to collect has over almost 15 years of data on the movements of these animals, the environments that these animals are experiencing, so the habitats, temperature, rainfall across the study system. And it also has an auxiliary data stream. So sensors called accelerometers were deployed on these animals. And this to date has largely been ignored, but we're going to circle back to this in a few minutes. And so this data spans this period of time where we've had these record-breaking temperatures, we've had extreme droughts, and we've had large year-to-year variations in things like precipitation, so rainfall. And so this is a really great data set to look at how movement is being impacted by these environmental conditions. But hunger is the overarching problem. And the problem with hunger is you can't directly observe it. So if you want to see where an animal is going, you put out a GPS tracker, you get the longitude and latitude, and you can plot it. But it's really difficult to get at how hungry an animal is from a sensor that you put out. So if any one of you here have used a Fitbit or a smartwatch or even a fitness ring like an Aura, they might have a sensor in them that's called an accelerometer. And these sensors are really good for measuring the behavior and getting a proxy for energetics. And so in our study, we put out accelerometers onto these animals to try and get at hunger and energetics. And for those of you that don't know, an accelerometer is basically a sensor that measures changes in acceleration across different planes of movement. And why it's really exciting for us and hunger is because it can be used to estimate two key metrics. You can use accelerometers to get a measure of energetic output, and that's because you have this pre-calibrated relationship between acceleration metrics and energy output from other studies. But you can also use accelerometers to get a measure of energy intake. And that's possible because if you look at the raw data from an accelerometer, you see different patterns. And different behaviors have different patterns within that accelerometer data stream. And so if you can learn what different behaviors look like in that data set, then you can get at what the animal was doing when you're not with it. But you first have to learn what those different behaviors look like. That's not really trivial. If I told you to look at that and tell me what those behaviors are, you probably wouldn't be able to do it. I can't do it. And so the way that you get around that challenge is you go out and you record instances of the animal doing the behaviors you're interested in when you had the accelerometer out. So you want to collect snippets where you know for a fact what the animal was doing for the behaviors of interest. You repeat this many, many, many times for the behaviors that you want to classify. And if you do that enough and you give that data to AI models, theoretically, you can train those models to detect behaviors when you weren't with the animal at all. So you need this labeled data set, and you can use that to train these models. But for wide-ranging species like the African wild dog, it's really hard to collect that data. And so over the last 2 years, our team, which includes members of the Abrams Lab and researchers from Botswana, have been attaching microphones and accelerometers onto African wild dogs. We then follow them in a Land Rover with a video camera, like some sort of paparazzi, and we collect lots of labeled data for what these animals are doing. And so over the last 2 or 3 years, we've collected an immense amount of audio data and video data where we know for a fact what the animal was doing, which were then labeled by undergraduate helpers who were immense. So we use this to create this textbook of labeled data that we can use to train models. The challenge is that applying that to the AI models is not trivial. There's a lot of different problems that come up. And in ecology, there have been 4 big things that have mainly hindered the widespread application of these models. And the first one is the class imbalance. And this basically refers to the fact that you have more training data for certain behaviors than for other behaviors. So if you wanted to collect this data in a lab setting, you would ask someone to eat, to sleep, and to do different behaviors that you're interested in. But in the wild, these animals are heavily biased towards sleeping. So when you go out there, all you collect is sleeping data, and for all the other behaviors you're interested in, you get a relatively small snippet of it. The second problem is quantifying uncertainty. With these models, you often get like one classification: feeding, sleeping, resting. You don't get a measure of how certain the model was for that behavior. And so you just kind of have to take it at face value, which is problematic. Third, you have this problem of generalizing the model and whether the model that you train on one set of data is applicable to another set of data. For example, if we train the model on African wild dogs from 2012, and then we collect more data in 2015, is that still going to provide classifications that are accurate and that are relevant? And then fourth, these models just make these classifications on isolated windows of the acceleration data stream. They don't consider what the behavior was before or after. They just look at that one snippet in isolation. And as you'll see from Medha a little bit later on, it reads these really erratic behaviors where the animal was sleeping, feeding, resting, which doesn't make any ecological or biological sense. And so now Medha is going to take you through the how we went about addressing those 4 challenges, and then I'll pop back in a little bit later on.
Thank you, Gas. All right. Hello, everybody. Yes, I was already introduced. I'm Medha. I work with the Harshvi Lab. And our goal with this amazing data that Abrams Lab brought us is to really take the data to the surgical table and understand what can we do about it, and kind of try to use AI to solve these problems of biologging, where the animal is doing something and we're getting data from some accelerometer, and the signal is coming to us online, and someone sitting in a lab should be able to tell the animal is sleeping right now, the animal is awake, is eating right now. And these kind of things we should be able to do them from a lab setting. And so what is really important is to have representative data that we call training data, and train some models on this data where we know we have a labeled data where we have the accelerometer signals, and then the signals matched with the behaviors, and we train the model on that. And then later on, we give the model accelerometer signals without any label, and we hope that the model gives us not just valid predictions of the behavior, but also how certain the model is about that prediction. Because what if the animal is sleeping versus sitting? There's not a lot of difference that happens in movement when the animal is stationary, regardless of what activity it corresponds to. So we want the model to also say how certain it is when it is making these predictions. So motivated by some of these problems that Cass just discussed, we are going to go over how we tackle these problems, and then look at the performance of our models on this particular African wild dog data. Yeah, okay, so let's dive in. So the story begins with an accelerometry signal. This is, for example, an x-axis. There are three axes, x, y, and z, and this is the accelerometry signal along the x-axis. What we have for this data is time-stamped behavior labels. So we know from one duration to another, the animal was moving, eating, running, and this is the data that is collected via either video recordings or audio recordings, and someone labeled the behaviors from these recordings. So the first thing that we do is we extract the signals that we know correspond to certain behaviors. So we separate out, for example, in this case, moving, eating, running, and now we know that from this duration to this duration, this signal corresponds to this particular behavior. And then once we have these signals, of course, they are going to be of different durations. For example, here, the eating happened for much lesser duration compared to running or moving. So, but the machine learning models, they require some standard format of the data. So in order to standardize it, we take, for example, the moving in this case, and then we split it into several fixed duration windows. For the African wild dog data set, we chose 12 seconds because we found it's quite representative of each behavior. For animals with slower movements, for example, a cow or someone, that duration might be longer because they take longer durations to express a behavior. But for African wild dogs, 12 seconds seems like a good window duration. We split the signal in 12-second durations and then extract these pairs of accelerometry signal, window, and the label. And with this process, we are able to construct 23,368 pairs of matched signal windows and behavior labels. Across these 5 behaviors that we are interested in, namely feeding, moving, resting, running, and vigilant. With these label, now with this standardized data set of besides 23,000, we look at the class distribution, which is one of a very important obstacle one would face when using real life ecological data. Here you can see that running, for example, or feeding is of much lesser duration compared to other behaviors like sleeping or resting. So the goal is to how do we tackle this issue? If I take this data set and train a machine learning model on this, I will get very less predictions of feeding and running, which happen to be one of the most interesting behaviors for the analysis. But I would, even when the animal is actually eating, I would not get those predictions because the model has not seen enough representative samples belonging to that behavioral class. So looking at this image, for example, the first row, the red dots, they correspond to the distribution of the data over these different behavioral classes. And what is ideal is the blue dots, where we have the uniform distribution or like equal probability mass assigned to each behavioral class. But the reality is the red labels. So what we propose is that we take a combination, a linear combination of these two distributions. So 1 minus theta times the red plus theta times the blue, where theta is what we will call the rebalancing parameter. And taking this linear combination of the two distributions, we end up with something which does not look so bad. The purple dots, yes, there is class imbalance, but it's not too extreme. So for example, if we take theta equals to 0.7 and we do this kind of partial rebalancing, we get a distribution over the classes, which is good enough. If we don't do any rebalancing, that corresponds to theta being equal to 0. In that case, we have no rebalancing, and we end up with the extreme class imbalance. And for theta equal to 1, it would be complete rebalancing, and we say for every class, we have the same amount of distribution. So what do we do in this case? We enforce this kind of rebalancing by repeatedly drawing the samples from that belong to the minority classes. Here in this case, the feeding and the running. And then we subsample or we sample the ones that are majority behaviors lesser. All of that is to say so that we end up at this purple distribution. So this is how we can flexibly attain a class distribution by tuning for the parameter theta in this case. So with this kind of rebalancing being applied to the training data set, how do we actually train a model to predict the behaviors based on accelerometry signals? So this is what the schematic of the model looks like. We have the signal on the far left. We have the signal on the far left for the accelerometry signal along X, Y, and Z axis. This signal is passed into something called convolution layers, which basically apply, think of it like a filter along the axis, along the one-dimensional axis of the signal, and convolves the signal and tries to extract features from that signal. And then we apply multiple such layers. Each time there is a filter which can be trained, and that filter moves along the length of the signal and then extracts features, and it does it over and over again to the point until we arrive at this flattened layer, which is basically an extremely long vector whose size we can determine by selecting or tuning for the model size. But in the end, we end up with this 1D flattened vector, which contains all the information there is in that signal about its class. So this is what we would call in machine learning feature extraction. We're trying to extract what is really important information in the signal. Once we have this these features in the flattened layer, we can do several things with it. Here in this case, since we are interested in the prediction task, which is to take this accelerometry signal and predict one particular class or assign a score to a particular class, we pass it through a fully connected neural network, which in the end gives us scores. So what ends up happening is we get scores for each behavioral class, which tells us something about the probability of success of each class. So here in this case, for example, if we pass this signal, we get much higher score for standing compared to running. And then using these scores, we can either choose a class which has the highest score and say that the accelerometry signal corresponds to that particular class, or we can do something more in the line of uncertainty quantification. So what do we do for uncertainty quantification? Once we have all of these scores, we want to know whether the most likely outcome, say, for example, standing, is the right classification, or there is something more? Is there more uncertainty associated with my prediction? And this is where prediction sets come in. What are prediction sets? They're basically a set of classes which represent that there are a set of classes which tell us that the true class belongs to this set with some pre-specified probability. So here in this case, what we're saying is that the label Y belonging to the prediction set, here in this case, a couple of behaviors, given that that I have observed a particular accelerometry signal, that probability is greater than 0.9. So I want to train a model which gives me this prediction set instead of the most likely outcome. And the way to do that is to take these scores that are output by my classification model, the one using convolution layers, take these scores and train another model on top of it, which takes these scores as input and gives me a prediction set and assures me that my true class belongs to this prediction set with some pre-specified probability. And these prediction sets are called regularized adaptive prediction sets, just a technical term for how they ensure that this condition of the true class belonging to the set with probability 0.9 or whatever pre-specified probability it is met. So these are what we acronymize as RAPS or RAPS. And these are the prediction sets that we propose. And the model outputs these sets instead of one most likely outcome. And then the predictions look something like this. For each signal, or for each this 12-second window that is input into the model, it returns us a set. So for example, here in this case, the model is much more certain about moving when it receives that particular moving signal versus when it receives this resting signal and the model is confused between resting or vigilant. Because in both the cases, the animal is stationary. It's just that in one case, the animal is lying down, and then the other one, probably the animal is sitting or standing. But in both cases, it's stationary. So from a movement point of view, there's not much difference over there. And that's why the model is confused. So we would like to be aware that the model is confused instead of being misled and think that the model is resting right now, whereas the model is half as is almost half as sure for it to be vigilant instead of resting. And similarly, in the case of vigilant, where the model is again confused between vigilant and resting, whereas it is quite sure about running and movement and moving, these kind of behaviors. All right, so we have tackled the problem of class imbalance, and we have tackled the problem of uncertainty quantification, where the model does not mislead us with one classification label when it is confused. The third is the distribution shift. What happens, and this is a characteristic of the data that we are working with, but also more generally in real life, where the data is collected, for example, in 2015, and then now we want to apply the model on this same trained model on data from, say, 2025. And we want to make sure whether the model is going to give me the same classification accuracy 10 years later or not. Or the other way this kind of distribution shift might happen is when the model is trained on a group of animals, and then it is tested on another group of animals, which might have their own unique ways, maybe, of expressing those behaviors, but we want to capture whether the model can understand that variability and is able to maintain performance throughout. So yes, so the model performance can decline due to the distribution shift when the characteristics between the training and the testing data are different. So there are, in the data set that we have, the African wild dog data set, we could recognize 3 different ways where the model could decline in performance on the test data. One is, since this data is collected from a variety of different individuals, variety of different African wild dogs, we want to make sure that the model generalizes well to different individuals. This setup, this experimental setup, we call it interdog, where we want to test whether the model is robust towards differences in individuals. The second is inter-year. The model is, the data is from 2021 and 2022, and we want to make sure that the model generalizes well across this year gap. And then the third is what we call inter-ANPM. The data is collected in 2 phases, the morning phase and the evening phase, and we want to make sure that there are no differences. There's nothing specific that the model is learning about, whether it's morning or evening, or whether it's the year 2021 or 2022. The only thing that the model should be extracting is the features corresponding to the accelerometry signal and nothing else. So we create these 3 different kind of splits, and we test whether the model generalizes well to all of these 3 different settings when we differentiate the training and testing data based on these parameters. And then the fourth issue that Cass discussed is the temporal context, where we want to make sure that we do not have any of these abrupt classifications where we say the animal is eating and sleeping. It doesn't make any sense for the animal to immediately fall asleep and then immediately start eating again. So we want to make sure that the temporal context is well understood. So for that, what we do is, if we look at this accelerometry signal, this is from one particular day in the life of an animal, and we see that for this accelerometry signal, we have labels that are available for certain time points. But if we look at the predictions that are made by the model, on the y-axis, we have the scores for different behaviors, the 5 different behaviors we're interested in. And on the x-axis, we have the time. And what we see is, depending on the darkness of the blue color, we see the scores that are assigned to each particular behavioral class at different time points. But we do see these abrupt changes that are happening abruptly for a specific time. A behavior gets high score, and then immediately after that, it does not. And we want to smoothen these things out. We want to understand whether it's actually just a kink, or is it actually representative of reality. So for this, what we do is, suppose we have scores, again, for the moving behavior. These are the scores that are available to us for different windows of 12 second, 12 second, 12 second each. And lighter represents less score for moving, darker color represents higher score for moving. Instead of looking at just the score for the 12 seconds, we would like to average them out over several windows, and the number of windows we can average out is a tunable parameter by anyone who's using the models. But we would like to average these out, and then this averaging window keeps moving towards the left, and so that we obtain the average scores across, here in this case, 5 different windows. But again, this is a tunable parameter. And in the end, what we get is a much smoother version of the scores compared to the one previously, which may have outliers, as it does in the case where we have a very dark navy color in the left. So once we have smoothened these things out, if there were multiple navies right next to each other, that would give us a sense that the animal was actually moving around this time. But since it happens to be a kink, it gets smoothened out. This is just a schematic for visual purposes. But if we look at the actual data and how this is done, so on the top, we have the score predictions for each behavior versus time on the top plot. But then after the smoothing with a window size of 10, this is the smoothened scores we get. And what ends up happening is that those abrupt changes we were noticing earlier, they get smoothened out, and they're still there if the animal was actually doing that thing for, say, 12 multiplied by 10, so 120 seconds. So these are the 4 methods we propose for the 4 different issues faced in an ecological context. And then we would like to share the results on how it performs on a data set. So for that, to actually evaluate the model on the actual data set, we would like to use some evaluation metrics. So there are the evaluation metrics can be classified into 2 parts. One is when we're just looking at the most likely outcome. So we receive those scores for each behavior class, and now we just pick the behavioral class which receives the maximum score. So how do we evaluate that if you're only interested in the top 1 behavioral class? So we can use something called precision, recall, and then an F1 score. Basically, precision gives us the true positives over the true positives plus false positives. So basically, of all the behaviors, of all the instances when the model classified them as feeding, how many were actually feeding and how many were just falsely classified as feeding. Versus recall is of all the instances that were actually feeding, how many were classified by the model as feeding. So that would be recall. So how many relevant items were selected. And then F1 score kind of combines these 2 information, where it is written as 2 times the precision multiplied by recall divided by precision plus recall. So this would be the evaluation metric for the most likely predictions. Similarly, we have the evaluation metrics for the conformal model, which gives us those prediction sets. So for the prediction sets, we can use 2 different evaluation metrics. The first is coverage, which means that recall how we trained the conformal model to display prediction sets that contain the true class with a probability of 0.9. So in the ideal world setting, when we deploy this model on the data, 90% of the times, the true class should have belonged in the prediction set output by the model, but that number is not exactly 0.9, but a slightly lesser. But the closer it is to 0.9, the better the model is. So that's why more is better. In fact, more towards that 0.9 number is better. And then the second is the average RAPS RAPS size, which is RAPS is our prediction set. And the reason it is important is because it signifies the precision with which we are predicting anything. For example, if we are classifying between among 5 classes, a prediction set which would have perfect coverage would be the prediction set which contains all 5 classes. So my coverage is perfect, it is 100%, but of course, the precision is bad because the prediction set size is too much. So less is better. So we want the average size of a prediction sets to be small to get as precise of predictions as possible. Hopefully, we want the model to say with absolute certainty that, or as high of certainty as possible, say that with 0, I'm 90% sure that the prediction, the behavioral class is this, but sometimes it gives 2, sometimes it gives 3 if it's very confused, but less is better. So finally, now we have one of those evaluation metrics, specifically the F1 score on the y-axis. And on the x-axis, we would like to tune for our parameter theta, which is a rebalancing parameter. Recall the rebalancing parameter helps us alleviate the class imbalance. And we would like to know how much I need to artificially resample from my data set so that I achieve good performance. So here for all of those 4 experiment setups that I described earlier, one where there is no split, the interdog, inter-year, and inter-AMPM. For all of those train and test splits, what we do is we try to tune for this parameter theta and basically see how much rebalancing is required for each of these experiments to give us a good enough performance in terms of F1 score. And for that, we see that when we don't differentiate between our train and test set that much. A rebalancing parameter of 0.7 is enough. For some experiments like interdog and inter-year, we need more rebalancing. There is higher class imbalance in those 2 experimental setups. And then for the last one, we again come down to approximately 0.8. So basically, this parameter theta, it needs to be tuned for every experiment before we actually train the models. All right, so now for one of the experiments, which is the no split experiment, where we do not split the data in any specific fashion across the train and test set. We compare the performance of the models in its most likely prediction for no rebalancing versus the rebalancing with theta 0.7. And what we see in these confusion matrices, these tables, is the proportion of times something matched, the predicted label and the true label matched. So on the left plot, you see that the feeding and the moving behaviors were not predicted correctly or accurately with high probability. However, after we increase their representation in the training data by introducing this artificial resampling with a resampling parameter of 0.7, the performance goes up and is now meeting a very high accuracy of 0.87 and 0.89. So this is the strength of rebalancing in accurately classifying behaviors that are of maximum interest sometimes, but are least represented in the training data. And this is for the most likely predictions, but for this one particular experiment. But these are the results for all 4 of our experiments. You can see for all 4 columns, the no split, interdog, inter-year, and inter-AMPM. These are for all 4 experiments. And for the evaluation metrics, we have For the most likely, we have the precision, recall, F1 score, and accuracy. That's for the most likely prediction. And then similarly, we have the RAPS coverage and RAPS average size for all of them. We do not see, it's important to note, we do not see a declining performance for any specific one experiment. And that basically speaks about the robustness of a model to these train test splits that we could create artificially using the data. But it's important when you have this kind of ecological data to kind of wrangle the model, wrangle the data set in every possible manner, like we did with these 4 experimental setups, to really check for models' robustness against certain kind of distribution shifts that it might encounter when the model is actually deployed in real life on online data. Yes, so our coverage is, you can see, between 0.88, 86, should be, ideally it would be 0.9, but like I said, it's trained for 0.9, so it will achieve something lesser, and similarly for the other experiments. And then finally, what are the future directions? So recall, all of this is for the acceleration data. We are able to train models that are able to extract features from the acceleration data. And now these features, if you put them in a prediction model, they are able to predict or classify the behaviors. However, if you put these features in, say, I want to impute the data, I have a string of accelerometry signal, but part of it is missing. So I want to know what happened in between. The extracted features can be used to train an imputation model. So all of the core of all of these machine learning tasks rely on a good feature extraction from the data in hand. And what we have is good features from the accelerometry signal. However, the data that we have from African wild dog and other animals, it contains other modalities. For example, one that is immediately available is audio data. So for different behaviors like running, lying down, stationary, eating, we have sounds like this, louder. But this is basically the audio of an animal eating, of an African wild dog eating. And now think about situations where our the model trained on accelerometry data really struggled for the and that was differentiating between resting and vigilant. Where the model is stationary, the movement does not give us much to differentiate between those two behaviors, but maybe audio can. Maybe there is a very specific audio profile associated with resting versus vigilant. And then there's our other modalities, GPS and other things. That's not really the point over here, but the thing is that with these different data modalities, we should be able to extract features and then plug them into an AI model, which is able to take different features from different data modalities and train an overall classification or overall imputation model. So here we have this model that does feature extraction for acceleration data, but then we can have audio data represented using the spectrograms on the bottom left. And then there is a machine learning model that allows us to extract features from the audio data set. These extracted features can be concatenated with each other and passed through a neural network, again, to, for example, here in this case, do a classification task for these different behaviors. Yeah, and that's a very exciting future direction for us.
So from an ecology perspective, we started working on the African wild dogs, and we've collected a lot of data from them. And now we're starting to expand to some of these other species. So in a few months, myself and graduate students from the Abrams Lab are going to be going out, and we're going to start collecting a lot of the data we've been doing for the dogs with the lions as well. So the idea is we've started with the dogs, we now want to expand to these other species. And once we have these models and they're robust, our plan is to then extrapolate them back to the historical data that spans all the way back to 2011, and to build up this data set of not just where these animals are going, but also what they're doing in those areas. And so once we get to that stage, we have almost 15 years of data-driven, environmental, and energetics data. This allows us and collaborators to tackle this huge question about how these different pieces are coming together, drive movements in these animals, and what that means for their survival. So we have this huge amount of data now, largely thanks to the efforts of our collaborators and different members of our lab that have spent years and years out in the field site, putting out these sensors, following these animals, and then afterwards creating the models to make sense of all the data that we're getting. We don't have enough time to tackle everything that we can do with this. So if anyone has in this room or in Zoom has listened to this talk and thought about any interesting research questions or thought about ways that some of the things that we're thinking about might apply to their own topics, either speak to Brianna or I or Medha at the end of this talk, or feel free to send us an email. We're always interested in hearing ideas and just chatting. We're particularly interested in if you have any ideas about the audio. We have like hundreds and hundreds of hours of this data, and we don't really have many plans to use it beyond the accelerometer classification. So if you have any ideas, just reach out. We'd love to chat with you. If anyone is interested in more generally about hearing about some of the work that we do, our research group was featured in a documentary on Apple TV called eScience. If anyone is dubious about how hard the work is, the very first scene of our research for this documentary is me driving into a hole, finding African wallows. So we get a taste of what it's like out there. This work was only possible through like the efforts of all the collaborators on this project. And if you want to reach out to any of us, feel free to pop us an email or talk to us after this. But also to the collaborators that weren't directly involved in this project, but are integral to the larger data collection efforts. And of course, to the eScience Institute and all the other various funders that have supported this project. Thank you for your time. If you have any questions, we'd be happy to answer them now.